this problem will help refresh our brain on some of our series tests. So this first one says, show that the series of the summation from n equals 2 to infinity of 1 over n squared ln n converges. Okay, and so one test that we could use is the comparison test. And if we're looking at comparison, we would just kind of wipe away that part and compare it to 1 over n squared. If we can't do a direct comparison, then we'll switch over and do a limit comparison test. Okay, but I'm going to try a comparison test with the summation of n equals 2 to infinity of 1 over n squared, and that is a p-series with p equal to 2. So then you got to remember, okay, well, what does that mean? Okay, so if you look at your p-series test, we know that if p is 1, that's the harmonic series. Okay, if p is less than 1, then it would be like 1 over n to the negative 2, which would just be n squared. So if you're summing n squared, that's certainly going to diverge. Okay, so that's kind of a way to make sure you don't get the direction of these messed up. Okay, so 1's harmonic, you know it. If you try something less, like negative 2, you'd have 1 over n to the negative 2, which is n squared. If you try to sum n squared, that fails the nth term divergence test. So anytime p is greater than 1, then that's going to be the one where it converges. So this guy, p greater than 1, converges. So the question is this larger or smaller than that? Okay, so if you look at the summation from n equals 2 to infinity of n squared ln of n, we're dividing by this quantity, and from 2 on, if we do that, it's going to be smaller than the series that we're starting with. So if you're smaller than a series that converges, then you also converge. Okay, so our series is smaller than that series, therefore it converges by the comparison test. Okay, now you can kind of make sure if you want, you can graph ln of x. I'm kind of wondering, why did they pick 2? So if we just graph here, okay, see, they didn't want to be dividing by a fraction because that would actually make this number larger. Here you're at 0, but 2 on, you're definitely dividing by a whole number and making that overall quantity smaller. So you can at least say it's true for that particular range that they gave us. Okay, now it just says to show this. Okay, well that looks like algebra to me. If they start with this side, we know from our rules for logarithms, spread out addition condenses to be multiplication. So we can do that. And then we can just distribute our n. So that would be n plus, the n's would cancel, 1, which is what they wanted us to show. Okay, so using this result, so they really just wanted to kind of lead us along the way. Using this result, show that an application of ratio test fails to determine whether or not that converges. Okay, so think back to your ratio test. Okay, you're finding the limit as n approaches infinity of the absolute value of the n plus first term over the nth term. And if they think that it's not going to work, it's going to equal 1, the one where we cry. Okay, and so if you're doing the ratio test, I've already written this here for you. That was not there. Okay, so the test question ended right there. We're going to have to remember that. Okay, and so we're going to do the limit. That's less than 1 would be convergent, and then greater than 1 divergent, equals 1 would be fail, you cry. Okay, so here we go. The limit as n approaches infinity of the n plus first term. So that would be substituting n plus 1, where we see an n into this. So we would have 1 over n plus 1 times the natural log of n plus 1. And then it's divided by this itself, which would be times the reciprocal. So I'm just going to go ahead and do that. Okay, so that would be like over 1. So then we would have the limit as n approaches infinity, n times the natural log of n over n plus 1 times the natural log of n plus 1. Now, I'm actually going to go a little bit backwards here, because if I look at what they asked me to prove right here, I recognize that this is here, and they said using the result surprise, they didn't say hence. So I'm going to go backwards and say that this is equal to that, and hope that it helps me. Okay, so that's my next step here. So I'm going to do the limit as n approaches infinity of n ln n over n plus 1, and expand this guy back out to what we had started with in the previous part of the problem. Okay, and then what I'm going to do is sort of look at these separately, see what I can figure out about this and separately from this part. Okay, so I'm going to do the limit as n approaches infinity, the absolute value of n over n plus 1, times, it's a property you can separate with limits, natural log of n over natural log of n plus natural log of 1 plus 1 over n. Okay, now this guy, as you go towards infinity, you can just use your horizontal asymptote rules. The degrees match, so this just goes to 1. Okay, and then this guy, as you go towards infinity, this is going to go to 0. Okay, so the natural log of 1 is going to be 0. So you end up with the limit as n approaches infinity of ln of n over ln of n. Okay, and so that is just 1 because it's anything over itself. And that is inconclusive, which would normally make us cry. I don't even remember my usual cry face, but it doesn't make us cry this time because that's what they wanted us to show, so we're happy with that. Okay, so they're like, okay, if you can't do it that way, they're kind of leading you. They knew you might try that, but they're giving you marks for it. Okay, so it says state why you can use the integral test to figure out this same thing. Well, they just want you to state what it is that determines you can use the integral test, which is that the function is a continuous positive decreasing function. So you're just going to say that. You're going to say that this guy, and you can graph it, kind of take a look at it at this point, make sure, positive decreasing function. And I'm going to go with for x greater than 2 because they picked 2 for a reason there. Okay, so I'm going to assume that as I move forward. And then it says hence determine the convergence or divergence. So they're clearly leading us hence to the integral test. So we're going to integrate this from 2 to infinity. We normally do 1 to infinity, but they started this at 2. I believe I did this, possibly this very same example, and we kind of looked a little bit at the graph and what happened around there. Something about ln of 1 is 0, so we would have an asymptote here, so they started at 2 to make sure we had that continuous function there. Okay, so I think I might have even had the same one on our practice for integral test video. So when we look at this, this is maybe it's got a little bit of a twist to it, because if u is ln of x, then our du would be 1 over x, and that's fine. But you really want to write it kind of like 1 over x is in the numerator. Okay, so it's like u is ln of x, and your du is 1 over x. Okay, so we can see we've got the makings for some ln's here. We do need to change our bounds, so let's make this the limit as b approaches infinity, the integral from 2 to b of 1 over x ln x dx. And this is my du. So we go 2 to b is du over u. So this is just ln of the absolute value of u, but I do know I'm in the positive realm, so I'm just going to go ahead and do just ln of my u, which is ln x. Who doesn't love a double ln? No one. That's the answer. I know you were wondering. From 2 to b. Okay, and so we would do the limit as b approaches infinity of the natural log of b minus the natural log of 2. Not too worried about that, that's a constant. This guy, you think of ln of x, it certainly goes to infinity as x goes to infinity. You always have your calculator when you're on paper 3. You could just graph natural log of the natural log of x. Look at it as it goes towards infinity. It's just kind of flattened out our ln x typical graph. But it slowly but surely is going to infinity. And so if this guy goes to infinity, so we would just say that the integral diverges, therefore the series diverges by the integral test. And just remember, you can always look at the curve. Another favorite of theirs is arctan x. So just remember that arctan x basically looks like this. As it goes towards infinity, it flattens at pi over 2. And towards negative infinity, it flattens at negative pi over 2. And so that's one that you might see on an integral test. But you can always look at the graph, take a look at what's going